Hey everyone! Today we are diving into a very interesting question. Can Bitcoin be hacked? With all the hype around the quantum tech, let's now try to separate facts from the fiction. You ready? Let's go. Can Bitcoin be hacked with a regular computer? Let's first of all talk about what is a private key in Bitcoin. In Bitcoin cryptography, a private key is a 256-bit number. What does that mean? It's just a string of 256 zeros and ones, like 10, 1001, and so on, like 256 characters in total, each either 0 or 1. Each bit is actually either 0 or 1. So in total we have 2 in power of 256 possible combinations. And that is a colossal number. It's such a huge number that it exceeds the number of atoms in the entire observable universe. What does a Bitcoin private key look like? To make it easier for humans and computers to work with these bits, they are written in hexadecimal, that is using digits from 0 to 9 and letters from A to F. Each such hexadecimal character represents 4 bits. So, to represent 256 bits in hex, divide 256 by 4 and get 64 characters. That means a 256-bit private key will look like a 64-character string and in hexadecimal format. For example, you can see example on the slide. This is a Bitcoin user's private key. Of course, you should keep it secret and you own the Bitcoins. If you lose it, and it's gone forever. How is a public key derived from the private key? This mathematical operation is used. P is equal D times G, where D is our private key, actually our 256-bit number. G is a predefined point on our elliptic curve, and P is a result of multiplication of the public key, also a point on the curve. Multiplication here is not ordinary, actually multiplication it's an elliptic multiplication, which essentially means repeatedly adding the point G to itself D times. It's easy to do in one direction. From D we can get P, but in reverse, knowing only P, guessing D is impossible by conventional means. This problem is known as ECDLP, elliptic curve discrete logarithm problem, and the theoretical hacking method, brute force, we can try it. What if we try to guess D by brute force? We simply start with the number 1, plug it into D times G, compare the result to the public key, and go up from there 2, 3, 4 until we find a match. Here's what it would look like in a code. The code you can see on your slide. The code works, but only if the key is small. In practice, a private key is a random number between 1 and 2 in power to 256. That is approximately between 1 and 10 in power to 77. How long would brute force take? A full brute force search requires up to 2 in power 256 operations. But on the average, we will find the correct value somewhere in the middle, meaning after 2 to power of 255 operations. So with a 50% probability, we'll find the private key after half of the brute force search. But even that is very, very long. Let's imagine we have supercomputers. Suppose we have 1 billion 10 to power of 9 powerful computers. Each perform 1 billion, also 10 to power of 9 checks per second. In total that give us 10 in power of 18 operations per second. Now if we would divide 2 to power of 255 by 10 to power of 18, we will get 5.78 times 10 to power of 58 seconds. Convert to years and you will get 10 to power of 51 years. Now let's compare. Age of the Earth is around about 4.5 billion years. It's all about 4.5 times 2 in power to 9 years. Age of the universe, it's about double so much, and you would need 10 in power of 51 years. Even if you connect all the computers on Earth, you would still need billions of universes worth of time to guess a Bitcoin private key. So, as a conclusion, hacking Bitcoin with a regular computer is impossible. Not because someone forbids it, but because the math itself makes it impossible. Even if you search keys with a billion machines at a billion speed, you need time billions of times longer than the age of the universe. So, can Bitcoin be hacked using a quantum computer? What is actually the difference between a classical and a quantum computer? A classical computer works with bits, either 0 or 1. A quantum computer works with qubits. They can be both 0 and 1 at the same time. This is called superposition. Because of this, it can store and process much more information in a single step. But it's not just about superposition. A quantum computer also uses two more things. It's entanglement and interference. This allows it not just to check all combinations at once, but also using quantum physics to amplify correct answers and suppress incorrect ones. A simple example. To check 1 million options on a classical computer, you need 1 million steps. A quantum computer needs only one round. It checks all at once and outputs a probability that the correct answer will be found faster. Now let's talk about what is the Shor's algorithm. Shor's algorithm is a quantum algorithm created in 1994 that can efficiently solve two problems: factoring numbers used in RSA and computing the discrete logarithm used in ECDSA, the one used in Bitcoin. ECDSA is based on the equation, like I said before, P equals D times G, where D is a private key, unknown, G is a fixed point on the elliptic curve, and P is a public key, and it's known. On a classical computer, finding D from P and G requires brute forcing values. This has exponential complexity. Shor's algorithm on a quantum computer can find D in polynomial time. So now let's talk about how fast is Shor's algorithm. Classic computers solve the problem actually in 2 to power of n time, where n is the key length in bits. In Bitcoin it's 256. Shor's algorithm solves the same problem in n to power of 3 times. So for 256 bits, the number of steps will be approximately 256 times 256 times 256. It's around about 16 million steps. Yes, that's a lot, but it's not 2 to power of 256. Shor's algorithm is a theoretical quantum threat because if a power enough quantum computer exists, it can extract the private key from the public key in seconds. Now let's talk about how many qubits are needed to break a Bitcoin private key. Qubit count estimate. Shor's algorithm needs about 2 times n logical qubits, where n is a key length in bits. For 256 bit key, that's 2 times 256, it's about 512 logical qubits. But due to errors and instability, each logical qubit requires about 100 physical qubits with today's technology. So the total number will be 512 times 100, it's about 51,000 physical qubits. So how long would it take to break the Bitcoin with quantum computer? We know that Shor's algorithm performs about 16 million steps for a 256-bit key. Let's assume a quantum computer can execute 1 million steps per second, 1 million operations per second. Then total time would be 16 millions divided by 1 million is about 16 seconds. So theoretically, a quantum computer could hack Bitcoin in less than a minute, but only if it has at least 512 logical or 50,000 physical qubits. You can see here a Python code example of Shor's algorithm, factorization demo. This is actually not a Bitcoin hacking example, but a simple demonstration of Shor's algorithm in Qiskit for factoring the number 15. On large keys like 256-bit, this code doesn't work. You would need a real quantum computer with thousands of qubits and fault tolerance. Why hacking Bitcoin with a quantum computer is not possible yet? Now we'll talk about the most important question. If a quantum computer can hack Bitcoin, why hasn't anyone done it yet? The answer is in the details, and it's not about theory, but about practice. The problem isn't that we don't know how to hack it, but that we don't yet have the right quantum computer to do it. Now let's talk about what are physical and logical qubits. When people say that a quantum computer has, for example, 100 or 1000 qubits, these are physical qubits. These are real physical particles or elements that scientists can isolate and use as a unit of quantum information. But there is a big problem. Physical qubits are very unstable. They last only fractions of a millisecond. They can be disrupted even by a weak electromagnetic noise. They lose their quantum state. This is called decoherence. Because of this, you can just take 512 physical qubits and run Shor's algorithm. They would produce errors at almost every step. To deal with this, the concept of logical qubits was developed. Now, let's talk about what is actually a logical qubit. A logical qubit is an ideal qubit built from a group of physical qubits. It has built-in mechanism for detecting and correcting errors. Usually, one logical qubit is created from 50 to 100 physical qubits, depending on the correction method and the quality of the physical qubits. So, if we need, for example, 512 logical qubits to hack a Bitcoin private key, we need 512 logical qubits times 100 physical qubits, so it's about 51,000 physical qubits. And this is minimum estimate. In practice, you will you need 100,000 qubits, maybe needed if you want stability. Now let's talk about what is an error correction. It's a set of algorithms that allows a quantum computer to detect and fix errors in the operation of qubits. For example, one physical qubit drifts from the correct state. The remaining qubits in the logical group notice it, correction occurs, and the calculation continues without distorting the result. In theory, it's similar to a RAID array or ECC memory in classical computers. But in practice, it's an incredibly complex task. Because quantum states cannot simply be copied and rechecked directly due to the uncertainty principle. Why is this so important? Because Shor's algorithm requires thousands of sequential operations without errors. If even one operation is performed incorrectly, the result will be ruined. And without error correction, physical qubits have a very high chance of failing already at the first steps. That's why all existing quantum computers today are noisy. They are called noisy intermediate scale quantum. This means they can perform simple tasks but are not ready for large-scale computations like breaking cryptography. What do we have now? Let's talk about it. Let's take a look. As of 2024, 2025. Google have a quantum computer with 53 qubits. IBM has ones with 127, with 433, and also announced with more than 1000 qubits. But all of these are physical qubits without full error correction. That means there is not a single logical qubit that lasts long enough. No system has yet demonstrated full, robust error correction. There is still no architecture where thousands of logical qubits can work together. So, why can Bitcoin be hacked now? Even if someone builds a quantum chip with 1000 physical qubits, that will be insufficient. To run Shor's algorithm on a 256-bit key, we need about 512 logical qubits. That means from 50,000 to 100,000 physical qubits. And not just qubits, but stable, coherent, precisely synchronized ones. Such quantum computers simply do not exist yet. In addition, a full software implementation of Shor's algorithm for elliptic curves is still incomplete. The entire infrastructure is still being developed. Cooling, control, scalable architecture, synchronization of thousands of qubits. All of this is still very experimental. As a conclusion, I can say yes, Shor's quantum algorithm can theoretically break a Bitcoin private key, but only in theory. In practice, this is impossible today because we don't have the required number of qubits. The qubits we do have are too noisy. Logical qubits are not yet realized. Error correction is still in prototype stage. The infrastructure of quantum machines is just beginning to form. When will a quantum computer capable of hacking Bitcoin appear? Let's assume we already know that in theory a quantum computer using Shor's algorithm can break a Bitcoin private key in just a few seconds. We also know that this would require something around about 512 logical qubits and with error correction around 50,000 physical qubits. The question is, when will a quantum computer with such a power be available? To answer this, we can use an approximate growth model, similar to Moore's law, applied to quantum computing. Now let's talk about what is actually Moore's law. Moore's law was formulated in 1965. Its essence, the number of transistors on a chip doubles every 18 to 24 months, or roughly every 2 years. This law described the pace of growth in classical computing power during the microprocessor era. It's very important to understand Moore's law is not a physical law, but an observation of a trend that held true for a long time. Can Moore's law be applied to quantum qubits? Let's talk about it. While quantum computers do not develop as linearly as classical ones, we can make a rough estimate. Let's assume the number of qubits in quantum computers doubles every year. This is even more optimistic than classical Moore's law. But it helps to visualize the timeline. And now take a look at it. Initial data for calculation. Let's assume that in 2024 we have a quantum chip with 100 physical qubits. It roughly matches reality. IBM has already 433, but we'll use a rounded number. We need to reach 50,000 physical qubits. To calculate how many times we need to double 200 to reach 50,000, we solve the simple equation. 100 times 2 to power of n equals 50,000. This means we need about 9 years for the number of qubits to grow from 100 to 50,000, assuming it doubles every year. Now let's take a look. That's a year-by-year forecast. If we start in 2024 and the number of qubits doubles annually, so we get in 2024 100 qubits, 2025 200, 2026 400, and so on. So we will get in 2032 25,000 and in 2033 51,000 qubits. So by 2033 a quantum computer could theoretically reach the required 50,000 physical qubits. And at that point, hacking Bitcoin might become practically possible. If the problems of error correction and stable logical qubits are solved. What if growth is slower? We should understand that this is an optimistic model. In practice, each new step is harder than the previous one. The more qubits, the harder it is to maintain stability and control. Scaling systems with thousands of qubits requires not only hardware, but also breakthroughs in engineering, cooling, synchronization, and quantum networking. So, if progress doesn't double every year, but instead every 2 years, reaching the 50,000 qubit mark would shift closer to 2040-2045. Now, as a conclusion, if you go by Moore's law and assume the number of qubits in quantum computers doubles every year, then a quantum computer capable of hacking Bitcoin might appear around 2033. If development is slower, then closer to 2040-2045. But even under that scenario, we must remember the number of qubits is not everything. High precision of qubit operations is required. Effective error correction is needed. A software implementation of Shor's algorithm for elliptic curves must exist. All these technologies are still in deployment or development, so the actual time of such a breakthrough may be even later than the projection suggests. How can Bitcoin protect itself from quantum hacking? Let's say the day comes when a quantum computer can actually derive a private key from a public key. What then? Is the Bitcoin lost? The answer is no. Because Bitcoin is a living software project that can adapt, update, and defend itself. To understand this, we need to look at how Bitcoin's code is structured, who writes it, and how changes are made. So, let's talk about who actually writes Bitcoin's code. Bitcoin is an open source software. The main client is called Bitcoin Core. It is available on GitHub and anyone can view how it works or even suggest changes. But in reality, not just anyone can add code. There are core developers, maintainers, who review the quality of the code, discuss proposals, check for security, and accept or reject updates. The name of these people are actually public. They are well-known programmers and cryptographers. For example, Peter Thiel, Vladimir van der Laan, Marco Falke, and others. No one controls Bitcoin alone. It is a decentralized community that decides the future of the project through discussion and consensus. How are updates made in Bitcoin? Let's take a look to this topic. To make a change to the Bitcoin protocol, you have to go through a process called BIP Bitcoin Improvement Proposal. There are some steps to do. First one, a developer writes a BIP, a document describing what change is proposed and why. The second step, the community discusses it, evaluates the risks and benefits. The third one, the code is implemented in Bitcoin Core. The fourth one, users, miners, exchanges, wallets must accept the update and start using it. An update is considered successful when the majority of network nodes and miners, switch to the new protocol version. Otherwise, a network split may occur, or so-called fork, which is highly undesirable. So, if quantum threat arises in the future, developers can propose a new signature algorithm, and the community can approve and implement it. Now let's talk about how can Bitcoin be protected from a quantum computer. Bitcoin uses the ECDSA, elliptic curve digital signature algorithm, for signatures. This is an algorithm vulnerable to Shor's algorithm. The solution is to replace this algorithm with a post-quantum algorithm, meaning one that is resistant to quantum attacks. There are already developed and tested post-quantum cryptographic algorithms that are not vulnerable to Shor's algorithm. Among them, first one, crystal dilithium, a digital signature algorithm based on lattice mathematics, fast, compact, and already selected by NIST as a primary post-quantum signature standard. The second one, Falcon, also based on lattices but uses more complex mathematics and is more compact in size. The third one is Sphinx Plus, a hash-based algorithm, very reliable but slower and requires more memory, used as a fallback option. These algorithms do not rely on factoring or discrete logarithms, which means they cannot be broken by Shor's algorithm. How can protection be implemented? Let's discuss this topic now. If Bitcoin decides to switch to post-quantum cryptography, it will require replacing ECDSA with, for example, crystals dilithium, updating the Bitcoin core code, changing the way transaction signatures are formed, ensuring backward compatibility so that old addresses and wallets don't lose funds. This process is technically feasible. Bitcoin has already had major updates in its history. For example, Segwit in 2017 or Taproot in 2021. Updates go through community consensus and don't break the network. What happens when protection is deployed? Now let's discuss it. When the post-quantum algorithm is implemented, new wallets will create addresses using the new signature algorithm. Old wallets can be migrated to the new format. Even if someone gets access to a public key of an old wallet, hacking it with a quantum computer will no longer matter, because the network will only accept signatures in the new format. In other words, the network evolves and ceases to be vulnerable. As a conclusion, I can now say Bitcoin is not a static system. It is a flexible, upgradable protocol governed by a community of developers, miners, nodes, and users. When a real quantum threat emerges, Bitcoin will be able to promptly implement new algorithms, protect users' assets, remain a secure and decentralized system. That's why Bitcoin cannot be broken forever. It's like a living organism capable of adapting to threats and surviving in all kinds of conditions. Hope you enjoyed this video. If you did, make sure to hit the like button, leave a comment and subscribe for more. See you in the next one.